Okay, let's get into it. We're doing a deep dive today looking at the fundamental structure of physics. We're using Eugene Wigner's 1963 Nobel Lecture as our guide here. Our goal really is to unpack how physics breaks the world down into these three big categories: events, the laws of nature, and these things called invariance principles.
Yeah, and Wigner starts off with something that's, well, maybe a bit counterintuitive. He points out that physics is so successful because it's actually quite modest in its aims.
Modest, how so?
Well, it doesn't actually try to explain all of nature,
Yeah.
Its real strength, its great success, comes from focusing just on the regularities, the patterns in how things behave.
Right, so you start with the actual stuff happening,
Yeah.
the events. That's the raw material, the unpredictable bit.
Exactly. And the really big breakthrough, which Newton gets a lot of credit for, was figuring out how to separate those events, the initial conditions, from the loss of nature.
Ah, okay, so the laws are the patterns, the rules.
Yeah. Precisely. They codify the regularities. They tell you how things interact or change given certain conditions. Think Kepler trying to find exact orbit rules versus Newton finding the underlying law of gravity that governed the motion.
So the law describes the how, but not the what or when of the starting point.
That's it. The starting points, the specific positions, times, velocities, those are the initial conditions. Everything the laws don't specify.
And Wigner's take is that these initial conditions, they're often just random.
He strongly suggests that, yeah. Unless something specific sets them up, they seem to have this inherent randomness. So the laws are beautifully simple, but the starting points are, well, kind of messy and arbitrary.
Okay, so events are messy, laws bring order. What's the third piece? The invariance principles.
All right. If the laws bring order to events, you can think of invariance principles as bringing order to the laws themselves. They're like super rules.
Rules for the rules.
Sort of. They act as a fundamental check. A law of nature is only considered valid if the patterns it describes are consistent with these accepted invariance principles. They're like a quality control check for the laws.
Okay, I think I follow.
Yeah.
And you mentioned these lead to conservation laws.
Exactly right. Things like conservation of energy or momentum, they aren't just arbitrary rules we found. They drop out directly from these invariance principles. They have to be true if the invariance principles hold.
So what are these principles? Wigner highlights three geometric ones, right?
Yes. First, Euclidean transformations. Basically, physics works the same here as it does over there. Location in space doesn't change the laws.
Okay, makes sense. Move your experiment, same result.
Second, time displacements. Physics works the same today as it did yesterday or will tomorrow. The laws don't change over time.
Right, that also seems pretty fundamental.
Yeah.
Obvious, almost.
Well, yeah, those first two were sort of always taken for granted, you could say. But the third one, uniform motion. That one's different.
How
It says the laws look the same even if you're observing things from a system that's moving at a constant speed. That's not obvious from everyday experience.
Ah, okay. Like, perspective shouldn't change the underlying physics if you're just drifting smoothly.
Exactly. And nailing that one down again, showing it holds true, that was a massive achievement of Einstein's special relativity. It wasn't intuitive.
Okay, so that's the classical picture. Events, laws, invariance. But you mentioned this gets even more powerful in quantum mechanics.
Oh, absolutely. The invariance principles have, let's say, even more teeth in quantum theory.
Why is that?
It's because of the underlying math. Quantum states live in these things called Hilbert spaces, and the math is linear. This lets the superposition principle really shine.
Linearity, meaning you can add states together.
Yes, essentially. You can take any two valid quantum states, and you can form infinite new valid states just by mixing them together, superposing them.
Okay, and how does invariance tie into that?
Well, imagine you have a state that's a superposition of many possibilities, maybe pointing in all sorts of directions. If you then insist that the final state must respect rotational invariance, it has to look the same no matter how you rotate it. That requirement forces the outcome.
So the symmetry constraint simplifies things drastically.
Precisely. The only state that looks the same from all rotational angles is one with perfect spherical symmetry. So the invariance principle acts like a powerful filter, simplifying the possible outcomes or even the possible laws themselves.
Got it. So let's recap the structure. You have random-ish events. These are governed by laws, which capture the regularities. And those laws, in turn, must obey the invariance principles, these fundamental symmetries that give rise to conservation laws.
That's the hierarchy Wigner laid out. Events, laws built on regularities, and laws themselves constrained by invariance.
But Wigner also pointed out something a bit humbling again.
Yeah, he noted that even with this structure, We probably only know a tiny fraction of all the laws. We have, what, 4 or 5 fundamental interactions we know about? Gravity, electromagnetism, the nuclear forces.
And the complexity there is already huge.
It is. And Wigner felt this complexity suggests we haven't found the ultimate structure yet. The dream is still to find maybe a single deeper principle, a super invariance. Perhaps that explains why we have these particular laws and interactions.
So the search continues for an even simpler, more unified picture underlying everything.
That's the ongoing quest, absolutely. Trying to find that ultimate simplicity Wigner pointed towards.
A lot to think about there. If the rules we see are governed by simple constraints, maybe those constraints themselves come from something even simpler, something for you to ponder.